Okay, welcome back to this set of lectures on introductory quantum mechanics for life scientists and computational biologists. And let's begin this lecture by summarizing where we are and sort of say, set up the stage for a final discussion of the first part of the course. So far, what we have been doing is essentially revisiting classical mechanics by reintroducing some essential concepts of classical mechanics, which are first introduced within the context of classical mechanics and Newtonian mechanics. That is the concept of work, energy, angular and linear momentum, and their conservation. And we have shown how important this concept becomes anytime you need to gain information about a physical system without having to explicitly solve Newton's equation. We have also made one digression into the theory of interacting particles which represent a nucleus, say a proton and an electron, entirely framed within Newtonian's mechanics. And this classical theory of the hydrogen atom served two purposes for us in this course. The first purpose was illustrative and to show how powerful indeed the concepts of angular momentum conservation and energy conservation are whenever you have to apply Newtonian's dynamics to a non-trivial system. In fact, if you remember, using angular momentum conservation, we could transform a problem that originally was three-dimensional, so implicitly required three coupled differential equations to be solved, into an effective one-dimensional problem. And the second important result was that using energy conservation, we could understand under which condition the electron could be considered bound to the proton, and under which condition the electron can be pushed away or be just scattered by the presence of a proton. So in principle, the possibility of binding the electron to the proton might be viewed as evidence that classical mechanics does indeed predict the existence of the hydrogen atom. However, we also have mentioned this specific property of electromagnetic interaction that predicts that anytime you have a charge performing acceleration, and rotation is acceleration, then radiation is emitted. And still, according to Maxwell's law of electrodynamics, radiation carries energy. Therefore, the particle was losing its energy, and by losing energy, you lose angular momentum and energy, and the particle would collapse towards the center of the atom within a time scale that is extremely fast. So the main conclusion we had from the analysis of the hydrogen atom was actually that there is no hydrogen atom in classical mechanics for a time scale longer than just a few femtoseconds. So there's no way you can account for the existence of matter the way we know it now, just simply within the framework of classical mechanics. The last reason for going through that exercise is also to set the stage for a proper quantum mechanical theory of hydrogen atoms, which will be developed much later in the course. But when we will get to that point, we will make use of very similar ideas to exploit angular momentum conservation to reduce a three-dimensional problem into one-dimensional problem. So the same philosophy that we adopted in this exercise in classical mechanics will be transferred and re-proposed also later on in the course, when we will be equipped with enough mathematics and tools to define a theory from the hydrogen atom within full glory quantum mechanics. Okay, so having said all that, it is now time to sort of wrap up the discussion on classical mechanics. And we do that by introducing a more general formulation of set theory of classical mechanics, which is much more similar to what quantum mechanics ultimately will be as a physical theory. In other words, we're going to rethink classical mechanics in a slightly different way and reformulate it in an equivalent way, which is basically ready to be upgraded to quantum mechanics. So the transition to quantum mechanics will be smoother if we do it this way than if you completely start from scratch with a theory that bears very little things in common with classical mechanics. So the question that I'd like to sort of discuss with you virtually, unfortunately, this year, online, and we can discuss in the live meetings we will have following this lecture. The question I'd like to address is the following: what is a physical theory? And to be slightly more specific, what are the key ingredients which make a physical theory? And by ingredients, it means what does it take to have a physical theory? What is a physical theory made of? Now, these questions sound very broad and general and perhaps vague, to a point that probably many of you will be sort of stuck at the beginning of even asking the question, what does it mean to ask what is a physical theory? Where should I start asking myself this question? So I always think that understanding something consists of two steps: deconstructing false knowledge or partial knowledge to leave room, based on this experience, to reformulating things in a proper and more organized and perhaps deeper level of knowledge. So in this perspective, I'm gonna guide you in asking these questions by showing you that there's something we don't quite understand, even of the theory we think we understand the most, and use this discussion to rebuild. So let me be more specific. So let's start from the physical theory we're all supposed to know, Newton's theory. So let's say mechanics. Newtonian mechanics. Now, but if I were asking you, so what is Newtonian mechanics? What physical theory is Newtonian mechanics? Probably the answer that many of you will give is the physical theory described by the three Newton's law. And three Newton's law, are in principle well stated. Remember, the first law says that a body will continue in its motion in its state of rest or constant speed unless a force sets in, right? The second law is the famous F equal ma, which tells you how does the motion of a body change if it's subject to a force. And the third law says that anytime body A applies a force to body B applies a force to body A that is equal in magnitude but opposite in size, in sign. This is action-reaction principle. So these three laws, which I'm not going to write, I just focused on the second law, is together form what mechanics is supposed to be. But all these three laws contain loopholes if you think about it. First of all, you say a body remains a state of rest or constant motion unless somebody applies a force to them, which is some kind of difficult because it is only true in inertial frames, and inertial frames are those in which you're in relative velocity with respect to another inertial frame, which raises the question of, yes, but I need to define my first inertial frame in order to say that something else is an inertial frame, because given one inertial frame, a second frame is inertial if its motion is constant. Velocity is of constant velocity with respect of an inertial frame. And then you keep on going back, associated definition of frame to another frame, but you need the first element of the chain, that one inertial frame that everybody agrees this is inertia. And Newton's was sort of trying to get away with it by saying that stars were providing the inertial frame, but now we know that there's no such a thing as the fixed stars in the sky, in the heavens. They are, each of them, known inertial frame, gravitating, whatever, along their orbits. So the lack of an initial inertial frame already raises question of what is the first law, and what is the rest, and what is the motion. The first principle already sort of shaky. But the second principle and the third principle together, they're all subject to a very major weak point, and is, what is the force? The first principle says everything is in rest or in of constant motion unless there is a force. The second principle tells you how much acceleration you get from the force. And the third principle that gives you this force and reactive force principle. What is this object? Newton's theory doesn't say what is a force. Yet the entire Newtonian mechanics is based on the concept of force. What is a force? Now, at this point, when I'm giving this lecture in first person, live in a real class with physical students in front of me, I like to play an act. I typically walk out of the room, have a couple of seconds outside the room, and then I go back into the class, pretending I'm starting the lecture from the scratch, and I'm meeting the students in that very moment to say, hey, good morning. So now today we are here to discuss the concept of force. Tell me, what is the force? And typically when students are asked the question, what is a force, without having had the previous discussion like we had today, when you start from scratch and you ask somebody out of the blue, what is the force? 99% of the time their answer would be, force is mass times acceleration. And again, this is nice because it illustrates a loop. Because Newton's law says that the acceleration is the force divided by mass, and the nature, but it doesn't tell you what the force is. And if you ask somebody what is a force, it will probably tell you that it's mass times acceleration. So we are going in a circle here. we have a problem. So there's something intrinsically ill-defined if you think about Newton's theory. So now we are ready to see that we think we have a physical theory in mind, but we don't quite know what we have in hand, because this physical theory doesn't have a proper definition of its main ingredients. So we need to sort of start over and rethink what is a physical theory and what does it take to define a physical theory. So in order to do that, let me erase the board completely and start over. So the first thing that makes a physical theory there are two, well, let's say three main ingredients which provide a physical theory. The first ingredient is the definition of the state of a system. So what do I mean by that? Well, a physical theory is about a system, some kind of a physical system, some kind of piece of nature I want to study. And the first thing we need to make sure it's clear is how we define the state of my system. Clear? If I don't have a proper definition of what is the state of my system, I cannot study the system, right? Because I don't know what it is. Now, in classical mechanics, a state of the system is the collection at some time t, because the system could change state as time goes by, right? It could modify its state. For instance, I take this little thing here and let it drop, and the state of the system, even intuitively, has changed. Before it was here, now it's here. So something has changed. So at some time t, in classical mechanics, a state of the system, let me call it gamma of t, is the collection of all the position of all the particles in the system. Let's suppose there are n particles. So I have 3. I have, but the position alone do not entirely specify the state of my physical system. Because you see, this physical system, time t, my particle is here, my collection of particles are still and are right here at this height. And this physical system are two different physical systems, two different states of the system. In the first case, the particles were at this height and they had no velocity. And if I let it go, it will drop, right? And in the second example, at time t, the position was the same, but the velocity was different, and the system will evolve differently, right? So depending on which state I am, my future will be different, right? So in classical mechanics, in order to define a state, it is not sufficient to define the position of the particle. You also have to define the velocities of the particles. Well, rather than defining the velocity, in classical non-relativistic mechanics, you might as well multiply velocity by mass and get what is called a momentum. In classical mechanics, this is completely equivalent because the mass is a constant, and therefore you can always, you're scaling velocity by a constant. Nothing really changes. When you get to speeds that are close to the speed of light, then you discover, and this is far beyond this course, that the mass is no longer constant, but the mass changes with a velocity, and as a result of which, momentum may not be the same as velocities because of this. Let me reshare the screen because there is a problem with sharing my Blackboard when I don't write for some time, so I have to go through this problem every so often. I will use a different Blackboard in the future, but okay. Now I recall myself why I was using the other Blackboard. Okay, so this is the collections of positions in the system and momenta in the system that compose the state. And this point here is a point in a space. You can look at all these coordinates as components of a vector. How many components there are will tell you in which vector space this state will be. And now if you count, there are 3 components per particle. So there are 3 times n, 3n positions, and 3 times n momenta. So this is really a 6n dimensional space. So the position, the state of a system in classical mechanics of n particles is made of 6n, is basically a point in a 6n dimensional vector space, and this is called the phase space. For historical reasons, which I don't need to emphasize here, why the word phase enters in this name is sort of historical, and we don't go into that. So we know now what is for us the state of a system. Just to give an example, if I have a particle in 1 dimension, 1 particle, d equal 1, meaning I have a particle propagating on a line and can only move forward or backwards, very boring life. The phase, then in this case, I have 1 component for the position, there's only 1 coordinate, and 1 component for the momentum. So in total, my phase space is 2-dimensional, and I represent it this way. I call it X, and I call it P. So a point in this is a particle with position, say, x0, and momentum p0. So for instance, if this is x0 and this is p0, it's a particle moving this direction. Now, notation-wise, sometimes when you work with phase space, x, the position, is also denoted with q. You use the notation q for positions. These are actually something called generalized coordinates, but let's not be too general here. I mean, all these tools are used to, in a context of an extension of classical mechanics formalism called analytic mechanics, and they have a little bit more general definition. We are not interested in covering all that. We're interested in the essence here, is that for us, coordinates will be basically positions, and all we need to do is basically that. Okay. Now let's take a leap. We have now defined what is a state. What is the second ingredient of a physical theory? The second ingredient of a physical theory is a recipe to determine the system's equation of motion. What is the system's equations of motion? Is an equation that, given the state of a system at some time t0, can tell me what will be the state of the system at some later time. It sounds very intuitive, right? Equation of motion is what really provides the heart of the physical theory, because what do I do with the physical theory if I cannot make any prediction? Physical theory is about predictions, right? So, for instance, I know the initial position and velocity of the atoms, or if you want, of this cap here. I know, for instance, that is still in rest and at 1 meter from the floor, and using by solving some equations of motion, I must be able to find out what will be the position and velocity at some later time. And I can represent this in phase space for one particle in one dimension. You know, the phase space is a plane. We have a, now I'm going to call it Q, I'm going to call it P. My initial state is some state gamma T0, a point in phase space, which is basically Q of T0 and P of T0. And what I want to find out is how does this state evolves in time, so that at some later time I get a different position and a different velocity. So clearly, if you want to understand how a state evolves with time, you need a differential equation. Or stated differently, remember the concept of evolution in time is the concept of how the state changes in time. And what is the mathematical tool that implements the idea of change in time? Is the time derivative. Now, an equation of motion is basically an equation which I have on my left-hand side, the time derivative of my state, and on the right side I have whatever this equation will be. This will make the physical theory, being able to write the right-hand side. If I cannot write the right-hand side, I will not be able to make a prediction, and in essence, I will not have any physical theory. So really, the equation of motion is an equation that contains on the left side the state of the system derivative, and on the right-hand side, something that this derivative is equal to. Right? And just another bit of notation, which will become handy. Notation, once again. And the notation is, sometimes, since time derivatives will be becoming very popular in physics, in the rest of this course, we use a typical physics notations that is borrowed from mathematics. And anytime we have specifically a time derivative, not a space derivative, just time derivative, we denote this with a dot. So this is the same thing. So anytime you see me write gamma dot, I will write what I mean is the time derivative of gamma. And just for completeness, let me say that in physics, when you have a second order derivative with respect to time, you often denote this with two dots. Oh, sorry, that's gamma here, of course. Right, again, this is a definition. There's nothing to understand. It's just a piece of notation there. So, in general, physical theory requires a recipe to build an equation of motion. And the equation of motion is basically something that tells you what is the time derivative of your state. How does your state change with time? Now, in the specific case of mechanics, remember, in the specific case of mechanics, my state is made by positions and velocities and momenta. So what this d by dt of gamma really means for mechanics is a collection of equations, d by, or let me write it with dots, q1x dot equal, then I have q1y and q1z. That's for particle 1. So rather than write 3 scalar equation, let me just say I have q vector dot of t equals whatever it is, right? And then I have for particle 1 through particle n. And then, of course, I will need the same equation for p dot 1 through p dot n. So this is the left-hand side. And of course, we need the right-hand side. And we know the right-hand side somehow has to be Newtonian mechanics driven if we want to represent as a physical theory Newton's equation. So we have to make sure we understand the right-hand side from Newton's equation, right? Because we want a specific physical theory that is Newton's physical theory. So, but we know some of these ingredients already. For instance, we know that the momenta are actually velocities defined by masses, right? So the left-hand side here is the velocity of a first, second, third particles, because it's the time derivative of position. So these are velocities. Now, velocities are momenta divided by mass, right? Which means mq dot equals p, right, for each particle. So the first n vector equations are simply, I use a different color to emphasize that this is the missing part of the equation, that's where we use our physics knowledge, that the momentum is the velocity times the mass. So I can write p1 divided by mass, all the way through Pn divided by mass. Oh, that's good. I am able to write the first part of my equation of motion. The second part of the equation of motion is the part that is a little bit tricky, because you see, now let me make room here by erasing this part. So we say that, gamma dot, we said, is equal to, I'm using different color. Gamma dot is equal to q1 dot p1 divided by mass, all the way to qn dot, which is equal to pn divided by mass. And then I want p1 dot is equal to. Now, we would like, what is p1 is mass times time derivative of velocity, which is basically mass times acceleration, right? And therefore, we would very much like to write force acting on particle 1, force acting on particle n. which is what we have in mind if we want to be consistent with Newton's equation. But we don't want to do it this way, because otherwise we run into the same problem of having to define what the force is, which is not something it is easy to do in Newtonian mechanics, for the reasons we've been discussing previously in this lecture. So remember, the second ingredient of a physical theory is a recipe for building this the equations of motion, which is as unambiguous as possible. So we want a recipe that ultimately leads to Newton's equations, but it doesn't involve defining what the force is and having to run into this loop law as an abstract. So what I'm gonna sort of guide you through in a very superficial level of detail is what is known as Hamilton's formalism of mechanics. So what does Hamilton's formalism say? Hamilton's mechanics, Hamilton's formulation of mechanics. Hamilton's formulation of mechanics says the following. In order to define a physical theory, you start with the concept of states given by a point in phase space. We covered that already. And then a physical theory is specified by a mathematical function, which you have to guess. And it's called a Hamiltonian. And this mathematical function is a function of all the momenta in the system and all the position. Now I'm using this capital letter P and Q. P and Q. Capital P is actually the 3n vector of all the momenta in the system. And capital Q is the 3m momentum of all the positions in the system. So rather than writing P1, Pn, Q1, Qn in the argument of this function, we might as well use this simple notation. So that this is again the notation. So Hamilton's equation, Hamilton's function is a function of position. And what function is it? Now here I'm cutting corners because I want to keep this within the time of our course, the number of lectures, in order to give a proper, rigorous, full Gloria definition of Hamilton's equation. I would need many, many lectures. But at the end of this long string of lectures, for the practical purpose that interests us, I would come to the following conclusion that I'm going to write in a minute. So rather than going through all that very formal, very thorough discussion, here I'm going to just state the final point. And for us in this course, it will be good enough. Okay, if you're a physicist and you want to go into theoretical physics, probably you want to do all the tour because you learn a lot along the way. If you're a computational biologist, you probably don't need it. You better learn some, biophysics instead. Right? So let's state the ultimate thing. This Hamilton's function is basically the energy, is mathematical function that describes the energy of the system. So this Hamilton function is defined always in the following way. Sum for all particles, always in the cases of interest for us. So in classical mechanics, a physical theory let's see if we can renew it by, I'll solve the usual problem of freezing. Stop mirroring, screen mirroring, remirroring. Okay, it seems to be working out. So a Hamilton's function is a combination of two pieces. This term and this term. What are they? Well, let's look at the first term. Let me remind you what P are. P are velocities times masses. So if I explicitly write this, I discover that this part is actually velocity squared divided by 2, mass squared divided by mass squared. So you recognize that the first piece of Hamilton's equation is the kinetic energy. Okay, so now we have a function that is a sum of a kinetic energy and a scalar function of position. It is tempting to imagine that that this will have to do with the potential energy. But now, the connection with potential energy I put a question mark, will become clear in a moment. Remember, what are we after is a sort of a rigorous, well-defined definition of physical theory, and the Hamilton prescriptions for building a physical theory is, my state is a point in phase space, and the equation of motion of these point states are built from a function. You give me this function, or basically you give me what kind of view you're talking about, because this is just a kinetic energy. So if you specify this, then of course you specify h, because it's the only part that you need to specify. The kinetic energy is given. This doesn't need to be specified. No need to specify, because it is what it is, the kinetic energy. So in order to specify the Hamilton's function, you have to tell me what is this function. If you do, then we know the Hamilton's function. And if I know the Hamilton's function, I can complete the equations of motion of my system. Because the equations of motion, this is Hamilton theory. Equations of motion will be built in the following way. Q. So let's start from the pi. The derivative of the momenta will be the derivative of the Hamilton function with respect to solid. The derivative of the positions will be the derivative of the Hamilton function with respect to the momentum. Okay? Now I'm doing this component by component, so I don't have to write vector symbols here in gradients. This is for every component, so the x, y, and z. Right? So let's see if this is the case. Well, there are n particles. The partial derivative with respect to the momenta will only, if I apply to the Hamilton's function here, this will return precisely pi over m. So the first half of the Hamilton's equations are well described by this first prescription. Take the Hamilton's function and take a partial derivative with respect to position. And the time derivative of the momenta are built from the negative of the partial derivative of the Hamilton function with respect to position. Position. So these are Hamilton's equations. Now I'm going to show you. Now, so I want to emphasize that Hamilton's equation really solve the issue. What is the right hand side of this equation? Because this is the left hand side and this is the right hand side. Now the question that we need to answer is, are Hamilton's equation really Newton's equation consistent or not? Well, like I just finished describing, the first part is clearly Newton consistent because it's telling me that the velocity is nothing but the potential divided by mass. And the second part is telling me, oh, look, this is actually the derivative with respect to qi of the potential of the function u, which is a function of all the q's. Now, remember, the derivative of a potential with respect to a position with a negative sign is what we call the force. Remember? So we are already saying this previously in the course, that the force in Newton's dynamics, could be used to define the work, and the work could be used to define the potential energy. And then the relationship between the potential energy and the force was that if you could take the potential energy and you take the gradient and change the sign, you get a force. So in Hamilton's formulation, we don't take this tool. We say a physical theory is given by an equation of motion for the phase space points, phase space derivative, the derivative with respect to time of the phase space vector is equal to some right-hand side that you get from the Hamilton's function. And the Hamilton's function is the function that I defined here. So if I take the derivative as written in this equation 1 and 2, all I get is first half, the momenta of the particle, meaning simply that q dots are the velocities. And in the second half, I get the derivative, the spatial derivative of this function u. Now, for this to be a Newton's equation, then clearly u must be the potential energy. Now things start to make sense. So you want a physical theory, say I want a physical theory for nuclear force in classical mechanics, which ultimately is bound to collapse because nuclear force will be subject to quantum mechanics. But suppose we don't know that. Well, you need to write down the kinetic energy of all the nuclei, protons and neutrons, and the potential and a function u, which represent the potential energy. If you can write the Hamilton's function, you're finished writing up your theory. Because from Hamilton's equation, you can derive the equations of motion of your systems that are consistent with Newton equations. But I didn't have to introduce the concept of force. I only had to introduce the concept of Hamiltonian, which is God-given. Physical theory is defined by Hamiltonian function. I have to write this function. How do I know it's the right function? Well, I write the function, I write the equation of motion, I solve the equation of motion, I go to my friend in the experimental lab and say, can you verify these equations of motion? And he comes back to me and says, no, they're wrong. Okay, let me try a different function u. And you modify u, you write the new Hamilton's equation, you solve new Hamilton's equation, which are now basically Newton's equation. You get prediction, you go back to your experimental colleagues until he will come back to you saying, finally we get agreement with the experiment. Then you know that you've written the right Hamilton's function and you have the right physical theory. So the workflow would be define H, compute equations of motion, which I'll write this way. So basically Newton's equation. Again, have to do this very, very annoying procedure, having to restart. So we have to define H, compute the equations of motion, which are Hamilton's equation, solve the equations of motion, obtain or work out, use the solution to obtain predictions, of experimentally observable quantities. And finally, I'm going to write here, experimentally test the prediction. And then depending on that, you have like agrees, if there is agreement, then you're done. Your initial Hamiltonian was a good one, was not falsified by experiment, and you finished. You reached the point of finishing your physical theory. If there is no agreement, you have to go back on the Hamiltonian, redefine the Hamiltonian, recompute the equations of motion, resolve Newton's equation, reuse them to obtain workable predictions, retest them, and re-ask yourself, do they agree or not? This is the workflow. In this workflow, I never use the word force. I use the word Hamiltonian instead, which, of course, is a function God-given, but at least is a function I know to define. My physical theory starts from guessing out of the blue this function and try to refine it. That's what the physical intuition is. Remember, at some point in the course, I mentioned the fact that somehow work and potential energy and kinetic energy were concepts that were originated from classical mechanics, but turn out to be more general, more fundamental than the concept of force itself. And in fact, the Hamiltonian function involves a scalar function u to define the equations of motion. And you, given u, which you have to write in the Hamiltonian, that you can work out their gradients that is related to what in Newtonian mechanics are called the force. So in Hamilton's equation, the potential is in fact the fundamental object. And the force is a consequence of that fundamental object. So there's a substantial change of perspective with respect to the F equal ma picture that we have in mind when we studied classical mechanics in high school. Now, up there in the space of important quantities is the force, is the potential, and then you take the gradient of the potential when you write down Hamilton's equation, which we know we can call it the force, because if we want that to represent Newtonian's mechanics, it has to be the force. Otherwise, the equations of motion are not consistent with Newton's equations. So that's the scheme. When I said that a physical theory, and I asked the question, what are the ingredients? I mentioned 3 ingredients, and I only spoke about 2. The first ingredient, remember, was a definition of the state of a system. The second ingredient was a recipe to build the equation of motion of the system, and this idea of using the Hamilton's function and then getting the derivatives of the Hamilton's function in order to get equations of motion is exactly covering this main point. But there's a third ingredient that we implicitly used when we were working out this diagram here in this board. And it's physical theory also requires a way to go from the state of the system to observable quantities. So implicitly, we are assuming a third step, which means given gamma, the state of the system, I must be able to work out the prediction of some quantity that I can observe. And of course, this will depend on the state of gamma. For instance, an observable could be the height of my particle. This I can observe because if I can take a meter, I can actually stick a meter here and tell you at time t what is the altitude of the particle. And it's of course a function of position in this case. Actually, it is the z component of position. Or my observable could be the angular momentum of the particle, or because in principle I can measure, or the angular rotation of the particle. And I need more elaborate combination of position and momentum in order to obtain those observables. Now, in classical mechanics, this step is trivial, so sometimes it's not even quite necessary to include this third ingredient of physical theory, how to connect the state of a system to an observable, because the observable is a trivial. 99% of the time, if not always, the observable is just a function of positions and momentum. So it's just to specify the function of gamma you're interested in. But we shall see that the same three main blocks, definition of a system, equation of motion of the state of a system, and connection between states of the system and observable, will be transferred to quantum mechanics. Will be the same. There will be the same three blocks in quantum mechanics. Just the rules in which you define the state, its dynamics, and the connection with the experiment will be different. And unlike in classical mechanics, the connection between a state of a system and an observable is non-trivial in quantum mechanics. It is straightforward in classical mechanics, but as we shall see, it won't be straightforward in quantum mechanics. So that's why I emphasize these three main blocks. State definition, let me say it again, because it's important. State, equation of motion, and going from states to observables. This is an observable. So these three ingredients, which again are not seen in this screen because of my problem. I promise this is the very last time I use this method to do lectures. These three states, these three main blocks are the building block of classical mechanics, but will be transferred, will appear exactly in the same order in quantum mechanics. So this is what I was referring to when I was saying that classical mechanics can be framed in a framework, in a form that is ready to be exported to quantum mechanics. Because when defining quantum mechanics, all we'll need to do will be to define what is a state, which will be different from that of classical mechanics, to define how to evolve in time the state, and to define how to connect the state to observable quantities. This is the heart of introducing, so this is basically the core of what to define quantum mechanics will be to define these three steps for a new theory. However, this would happen a little bit ahead of time, a little bit later in the course. I think it's time to stop for a moment and wrap up what we've done so far. I am assuming that some of this concept might be fuzzy in your mind. So there will be a live discussion the next, at least one lecture, perhaps two, in which this will be reserved to the students in the University of Trento, in which I will, I'll be available for questions, and maybe also make one illustrative example of how you solve a physical system, starting from the Hamiltonian down to being able to make observations. How you go through, put all this in practice in one case, which is notable and non-trivial. So we will stop for a couple of lectures, approximately, in order to sort of familiarize with everything we have said so far. After we have done with that, then we'll be ready to move a significant step towards the quantum territory. And in order to do that, we will begin illustrating experimental evidence in some particular way, showing how and when predictions of this nice classical mechanics scheme go wrong. And this will open the door to quantum mechanics, because it will tell us, okay, now we understand this and this and this and these predictions of classical mechanics aren't agreeing with experiment, and instead of experiment is showing other prediction, other results, and we need to come up with a recipe to go through those 3 steps that is fulfilling 2 main conditions. First of all, it does agree with experiments that classical mechanics would not agree with. Otherwise, it's not a better physical theory. It's probably as bad as the other one. And second request, must give the same prediction of classical mechanics in the regime where we know that classical mechanics is working, because you don't want to get a new theory that works in a regime but screws up whenever the other ones was working. So you want something that is including the previous theory but more predictive. So basically, I'm sure this is not going to work, but basically he was trying to write on the board, but it's not working, but there's no time to resync at this point. Basically, you want your classical mechanics to be a special case of quantum mechanics. When you work quantum mechanics in large objects in large time, remember the diagram we drew in the first lecture, then the prediction of quantum mechanics must reduce to those classical mechanics, because we know that the classical mechanics has been verified in that regime. But when you extend to microscopic world, classical mechanics breaks down, and hopefully quantum mechanics will survive. But this is all to be seen in a future lecture. I think it's good point to stop at this lecture. See you also.